Now see the relation between nth harmonic voltage and fundamental voltage, so that we will know how to calculate the value of nth harmonic voltage. So relation between nth harmonic voltage and fundamental voltage. Relation between nth harmonic voltage and fundamental voltage. Let us assume we have a stator. Here I am representing this to be the stator, okay, and in this stator a rotor is being placed which carries DC, because of which you can say let this to be the stator and rotor. Rotor carries DC and therefore we have north and south, this to be the stator. Is it okay? So we have 3-phase stator as A, B, C. I am representing only the forward, or you can say group 1 conductor. So A, B, C, and this to be the rotor. Is it okay? Now please see. Let the diameter of the stator, or you can say diameter of the machine, be D, okay, and the total length of the machine be L, okay. Now we have a 2-pole, or you can say n-pole machine with this as a stator and rotor construction. The rotor is placed in the stator, okay. Now please observe, you can say, sir, the flux we have in the air gap of the machine, the flux density waveform is, we have this to be the flux density waveform for a 2-pole machine with this as north and south. If we go with the triple N third harmonic voltages, then that can be represented in this way. This is your fundamental flux density wave, and this is your triple N harmonic voltage, okay. So we have this as a third harmonic voltage. If this will be the magnitude of the fundamental, that is maximum, then third harmonic will have a maximum magnitude of phi m by 9. Similarly, fifth harmonic will have a maximum magnitude of phi m by 25. Now please observe, if we go with the average flux density, then you can say, sir, average flux density is equals to 1 by pi 0 to pi sin omega t d omega t. So you can say 1 by pi into minus of cos omega t from 0 to pi. So this will become 1 by pi into minus of cos pi and minus plus of cos 0. So you can say this will become, sir, and the maximum flux density is Bm. So you can say the maximum flux density is Bm. So this will become 2 Bm by pi. This is the average flux density corresponding to fundamental, okay. And you can say, sir, the effective, or you can say surface area, effective surface area of the pole shoe which is affected is area under the each pole, which is going to be effect this A. So area under each pole is, you can say area under each pole can be represented in terms of effective surface. So area under each pole, is total surface area upon number of poles. Total surface area is, you can say 2 pi r into L upon number of poles P, where r is the radius of this. So you can say where r is the radius of this, that can be represented as r. R is the radius of the machine and L is the length. So you can say, sir, this will be equals to pi dl by P. This is the area under each pole. So if we know about area under each pole, we can find average flux per pole. Average flux per pole. Average flux per pole. Average flux per pole. Average flux per pole, that is phi average per pole, is equals to, you can say sir, flux is equals to flux density into area of effective area, or you can say area under each pole. So average flux per pole will become pi dl by p into Bm. Is it okay? So this will be the average flux per pole. You can say sir, average flux per pole is equals to pi dl by p into Bm. Bm is 2 Bm by pi, that is average flux density. So you can say sir, this will become 2, or pi and pi will be cancelled out. So 2 dl by p into Bm is the average flux per pole for fundamental. Similarly, if you found the third harmonic, then average flux per pole for third harmonic will become 2 into dl by p into Bm of third harmonic. So Bm of third harmonic, and the number of poles for the third harmonic is 3 times of the fundamental. So you can say 3p. Similarly, for nth harmonic, you can say 2 dl by np into Bm of nth harmonic. Is it okay? Now please observe, you have the average flux per pole for the nth harmonic and this average flux per pole for the fundamental, that I am representing by this. For fundamental, and this one is for nth harmonic. Is it okay? Now you can say sir, we can find the ratio of these two as phi 1 by phi n. So you can say sir, phi 1 by phi n by phi 1, that is nth harmonic average flux per pole by nth fundamental flux per pole is equals to 2 dl by p will cancel out, and this will become 1 by n Bm of fundamental upon Bm of nth harmonic. Is it okay? So we have a relation between phi n of fundamental and phi n of nth harmonic. Now induced EMF for fundamental per phase is under root 2 pi f phi 1 into TPH Kc fundamental into Kd corresponding to fundamental. Is it okay? Now if you have to find the nth harmonic distribution factor, let it be assumed that distribution factor Kd1. So you can say sir, for nth harmonic this will become under root 2 pi f phi n into TPH into Kd nth harmonic. So if you found the ratio, you will find that En by E1 is equals to phi 1 by phi n into Kd1 by Kdn. Okay, the nth harmonic has an frequency of n times of fundamental. So you may represent here as Nf. Is it okay? So you can say sir, f by Nf is 1 by n. Further you may write it as sir, nth harmonic induced EMF by fundamental will become 1 by n into phi 1 by phi n is equals to 1 by n into Bm of fundamental to Bm of nth harmonic into Kd of fundamental to Kd of nth harmonic. Is it okay? So you can say this will be equals to 1 by n square times of Bm1 by Bmn into Kd1 by Kdn. Is it okay? So you may represent in this way. This is the relation between nth harmonic voltage to, please see, I have made the mistake, that is En by E1. So this will become Nf by f, that will become n times of this. So when n and 1 by n will cancel out, and you may represent in this way. So nth harmonic voltage to fundamental voltage is nth harmonic maximum flux density to fundamental maximum flux density into Kd1 by Kd of Kd nth harmonic voltage by Kd nth harmonic voltage by Kd of fundamental. So please correct it. Is it okay? So we can find the relation between nth harmonic voltage and fundamental voltage. When we have to find the nth harmonic voltage, E of nth harmonic voltage can also be represented as under root 2 pi Fn, that is nth harmonic frequency, into phi n into Kc of Kd of nth harmonic into Kc of nth harmonic. This is the induced EMF equation for nth harmonic voltage in distributed and short pitched winding. Induced EMF equation, induced EMF equation for nth harmonic voltage in short pitched distributed winding. Short pitched distributed winding. So you can say, sir, we have induced EMF for nth harmonic voltage, that you can also found in this term, that is under root 2 pi. Fn is, you can say, n times of the fundamental, and phi n is 1 by n square times of the fundamental into per pole. For per pole you can say, sir, if this is in terms of per pole, then this will become phi n by cube, phi by cube, because the nth harmonic will have n number of fictitious poles. So phi by n square is for the magnitude of the flux, amplitude of the flux you can say, and n for the number of poles. So this will become phi 1 by n cube into Kd for nth harmonic into Kc for nth harmonic. So you can also go in this fashion. This also going to be the same result. So you can also say this n and n will cancel out, and this will become 1 by n square times of the fundamental. So nth harmonic voltage is also 1 by n square times of the fundamental. Is it okay? So you may represent in this way also. Now please observe, but we can find the relation in this fashion, it will be more beneficial. Now please see, you can say, sir, induced EMF equation in short pitched distributed winding. Induced EMF equation in short pitched distributed winding. So induced EMF equation in short pitched distributed winding is under root 2 pi f into phi into Tph Kc into Kd. This is corresponding to fundamental. Is it okay? However, in case of where Kc and Kd are called as, where Kc and Kd can be represented as Kw, that is what we call winding factor also. So it is constant for a machine once the machine is designed. So you can also say under root 2 pi f phi Tph into Kw. Is it okay? That is what we call winding factor. So this is the induced EMF equation valid for the short pitched distributed winding. However, the winding factor is equals to 1 in concentrated full pitched winding. Is it okay? Kc is equals to 1 in full pitched winding, Kd is equals to 1 in concentrated winding. So keep this in mind. This is your induced EMF equation in case of space harmonics are present. If you have to find the per phase induced EMF, then that will become under root of fundamental induced EMF square plus third harmonic induced EMF square plus fifth harmonic induced EMF square plus so on. This will be your per phase induced EMF voltage in case of distributed winding, or you can say when the space harmonics are present. So if we cancels all these higher odd harmonic voltages, then your voltage waveform will approaches towards the sine wave. In most of the numerical, they say the winding is uniformly distributed. So when they are saying winding is uniformly distributed and they are not commenting anything upon the short pitching, it means that the short pitching is 1. You can say short pitch factor is equals to Kc factor is equals to 1. Is it okay? And most of the time they will not give the phase spread. Instead of giving phase spread, they just say single phase, 2 phase or 3 phase machine. So keep this in mind, that is very important for numerical. Keep this in mind that phase spread in single phase machine. Phase spread in single phase machine is always equals to 180 degree electrical. Phase spread in single phase machine is equals to 180 degree electrical. It means this entire half we have in this fashion. Is it okay? So phase spread in case of single phase machine, it is equals to 180 degree electrical. Okay. So you can say if this is your north and this is your south of the rotor, so north and south of the rotor will decide this upper half as north, lower half as south, and all these are connected in series. So these conductors are under the influence of north and these conductors are under the influence of south. In that particular case, phase spread is equals to 180 degree. So phase spread for single phase is equals to 180 degree electrical. Similarly, if the machine is of two phase, then phase spread in two phase machine is 90 degree. That is, in two phase machine you can say, sir, one phase is say A phase, another phase is B phase. So A phase, another phase is your B phase. Okay. So if this is represented in this way, then you can say north and south. So this is represented as 90 degree. So this is your 90 degree of phase spread. Is it okay? So in this particular case, phase spread is 90 degree. In this particular case, phase spread is of 90 degree. So in a two phase machine, you can say phase spread is equals to 90 degree electrical. And for a three phase machine, phase spread in three phase machine is 60 or 120 degree. This 60 and 120 degree is also called as 60 degree phase spread is also called as narrow phase spread, narrow phase spread, and 120 degree is also called as wide phase spread, wide phase spread. Okay, 60 degree phase spread is possible in case of the triplet harmonics will be avoided in case of wide spread. You can say in this case triplet harmonics are 0. Okay, however, the triplet harmonics are present in case of narrow phase spread. So if you have designed the 60 degree phase spread for a three phase machine, then 60 degree phase spread triplet harmonics are present, and 60 degree phase spread is possible in case of a single layer winding. With a double layer winding, only 120 degree phase spread is possible, and therefore you can say the double layer winding is designed for a double layer winding. If it is mentioned in the numerical that double layer winding, then it means the phase spread is equals to 120 degree. In case if the winding is not mentioned as double layer or single layer, in that particular case for a three phase, it may be a 60 degree or 120 degree. Is it okay? Now 60 degree phase spread, you can say single layer winding can only give 60 degree phase spread. However, a double layer winding can give 120 degree phase spread. 60 degree phase spread can give 60 degree phase spread can give double layer as well as single layer. However, 120 degree phase spread can only provide a double layer winding. In case of double layer winding, you can say one more point. In double layer winding, each slot contains two half portion of the coil. You can say each slot contains two half portion of the coil. In double layer winding, each slot contains two, or you can say two half portion of coil. Therefore, thus in a double layer winding, number of slots is equals to number of coils. However, in a single layer winding, each slot contains only half portion of the coil, only half portion of coil. Thus, number of slots is half of the number of coils. Okay. So, in case if the double layer is mentioned to you and the number of slots is given to you, so you know about the number of coils also. However, in case of single layer, the number of slots is half of the number of coils. Is it okay? I will go to the double layer winding in case of DC machines. So, when we study about the DC machine, then I will show you how the double layer windings are being constructed. The armature winding, this is the basic, actually this is the part of the basic rotating machines, and I have taken this part in this synchronous machines because nowadays most of the questions asked from synchronous is based upon the induced EMF and harmonic induced EMF. So, keep this all the points of this topic in your mind, this is very important. Maybe some numerical asked in gate or ESC from this part. Okay. Now, please see, you can say, sir, what are the advantages of the cording and distribution factor? So, advantages of the distribution and you can say short pitching. So, we know about the advantages of the short pitching. What is the advantage? The main advantage is the generated voltage waveform will approaches towards sine wave. Another one is the copper saving. What is the advantage of distributed winding? The main advantage of distributed winding is that in distributed winding better utilization of space, you can say, and some of the harmonics are avoided by the distribution factor, especially triplen harmonics in case of 3-phase machine. If we design with a double layer winding, it will automatically going to be cancelled out. Is it okay? So, keep this in mind, and I am going to show you the other advantages that are going to be we are obtaining from the short pitching and distribution factor. One more thing, in case of harmonic fluxes, if the harmonic fluxes are rotating at a speed, so you can say these harmonic fluxes are also producing the eddy current loss and hysteresis loss in the machine in the format of heat, and therefore the overall machine gets heated and efficiency of the machine is lowering down. So, if we avoid the harmonics by using this Kc and Kd factors, if we cancelling out the harmonics, then you can say the generated voltage waveform will be sinusoidal as well as the machine will remain in the reasonable you can say temperatures. So, the overall efficiency of the machine will be better. So, I am showing some advantages of short pitched winding and distributed winding. If you are writing ES conventional papers and you need to write in terms of in the theoretical terms as the advantages of short pitching and advantages of cording, then you may take these as a points. Now, please observe what happened with the short pitching. You can say the dominating harmonics, especially 5th and you can say 7th, will be reduced and EMF will become more sinusoidal. The first objective is to get the sinusoidal induced EMF that we can achieve by using the short pitching of the winding. Second one is saving in copper material in overhang. Definitely the conductors are, the length of the conductors are not changed, but by short pitching the overhang length required will be lower and that reduces the overall copper and thus reduces the overall copper loss, increases the efficiency of the machine. Further, iron losses are reduced because the iron losses occurs due to the you can say change in flux in a stator body. So, you can say, sir, iron losses depends upon the iron losses are eddy current loss and hysteresis loss, and they depends upon the maximum flux density. Maximum flux density depends upon the resultant flux. So, if you observe, the resultant flux is the flux due to the fundamental 3rd, 5th, 7th harmonics and so on. The dominating rotating harmonics are being avoided by these short pitching. So, 5th and 7th if reduces, then you can say the overall flux is reducing, the resultant flux is reducing. So, you can say maximum flux density is reducing and thereby it is reducing the iron loss. Thus, the efficiency of the machine will become more. So, since iron losses are reduced, thus efficiency is increased. Another thing is self inductance of the coil is reduced because The leakage reactance is due to the fundamental flux, leakage reactance is due to the third harmonic flux, leakage reactance is due to the fifth harmonic flux, all R comes into the picture. So if the harmonic fluxes are avoided by you can say by chording, by short pitching, then the effect of the harmonic fluxes are avoided, then you can say, sir, overall leakage flux is reduced, so leakage reactance drop is reduced, this improves the voltage regulations. So voltage regulation of the machine is improved. One disadvantage also of chording, disadvantage is that overall generated voltage will be slightly reduced, but it will be okay. We are intentionally performing this chording, this reduces the overall generated voltage by a small amount, but on the cost of these advantages, the small amount decrement in the voltage will be bearable. Is it okay? Now please observe the advantages of distributed winding. In the distributed winding, you can say effect of harmonics will be reduced, as we have observed that third harmonic, fifth harmonic, seventh harmonic, by proper suitable distribution you can eliminate the effect of harmonics, and thereby you can say the waveform of the generated voltage will be approached towards a sinusoidal. Next is your armature winding is mechanically balanced. If we only put here 3 windings, 3 phase windings in this way, then you can say the mechanically imbalanced, and if we have distributed throughout uniformly, then stator will be mechanically balanced. One more thing, that you can say effective cooling is possible as the temperature of stator, effective cooling is possible as the temperature of stator copper loss is uniformly distributed throughout the stator body. If we have only stator conductors in this fashion, that is concentrated, in case if we use concentrated winding, then in order to cool down we need to use more number of cooling ducts across this wire, and therefore if we are using more number of cooling ducts, then the effective reluctance path increases. Instead of being this at only one point, if the stator conductors are distributed throughout the stator surface, then because of the current flowing through the stator conductors, they are going to produce heat, and that can be effectively reduced by the cooling gas, and that cooling gas will be flowed through in this manner. So you can say, sir, the effective cooling is possible by these cooling ducts. So the overall temperature of the machine drops, and therefore the efficiency you can say increasing. Also iron loss is reduces, very similar to the chording, as thus efficiency is increasing, leakage reactance decreases, and therefore voltage regulation improves. So on the cost of, again the disadvantage of this distribution factor is also the induced DMF is slightly reduced. On the cost of induced DMF, we are getting these advantages, and the main advantage is to generate sinusoidal voltage is obtaining. So on the cost of a small amount of induced DMF, this will be bearable. Is it okay? So you can say, sir, these advantages are needed, so we intentionally perform the distribution and we intentionally perform the short pitching. Okay, now we will see lots of numericals based on this topic, and then we move towards armature reaction in synchronous machines. Okay.